All right, so we talked about certain alkyl chains as being common patterns. Another thing that you're going to see in a lot of these NMR is aromatic compounds. And remember, for us, when we say aromatic, for now at least, we're just talking about benzene, right? And so the hydrogens directly attached to benzene show up in a very specific area, around 6.5 to 8 ppm. And they're pretty much the only thing that shows up there. So if you see protons in about 6.5 to 8, chances are you have a benzene ring. Remember the other requirement of a benzene ring, if you have the formula, it has 3 pi bonds and a ring. So it also has 4 degrees of unsaturation. So anytime you see 4 or more degrees of unsaturation, the first thing you should be thinking about, oh, I probably have a benzene. Then take a look at your NMR. Is there something between 6.5 and 8? And if there is, then you have a benzene ring. Note that things coming off the aromatic compound are not at 6.5 to 8, right? So if you have this methyl here, this is only approximately 2.5. So it's only the hydrogens directly attached to our benzene ring. And so the coupling in the benzene ring is actually quite complex, right? It shows some complex patterns. And so we're not really going to take a look at trying to decipher these patterns, but there's some very useful clues. So if you have an area from 6.5 to 8 and you see 5 hydrogens, right, that represents 5 hydrogens, that means that you then have a mono-substituted benzene, right? Because then there are 5 aromatic hydrogens. If you have 4 hydrogens, that means that you have a di-substituted benzene. And now here, the symmetry of this molecule depends on how many substituents you have. So for example, if your 2 substituents are the same, then you have symmetry along this axis and symmetry along this axis. And so all 4 of these protons will be the same, and you will see 1 singlet peak corresponding to 4 H's, right? So if you see 1 singlet peak in the aromatic region that corresponds to 4 hydrogens, you have these kind of 1,4 di-substituted benzene where your 2 substituents are the same. If your 2 substituents are not the same, right, now we have kind of A and B here, we still have symmetry along this plane, but we don't have symmetry along the other plane. And so we have HA here and then HB here. And both of these will show up as a doublet, right? So HA will be a doublet, and then HB will be a doublet. So if you see 2 doublets, or depending on the NMR, you might see a small splitting in these peaks, so they're kind of like doublets of doublets. But if you see approximately 2 doublets in this aromatic region, that means that you have this 1,4 di-substituted pattern. Of course, if you have 4 protons in the aromatic region, it doesn't have to be this 1,4 di-substitution. You could also have 1,2 or 1,3. And so if your substituents here are the same, it's relatively easy to tell, right? These 2 protons will be the same, so that'll be 1 peak. And then these 2 protons will be the same, so that'll be a 2nd peak. Whereas over here, this proton will be different. These 2 will be the same as one another, and then this one will be a 3rd one. However, these are going to kind of get mixed up a little bit, and so it's going to be very hard to tell between these 2 compounds, especially if you have 2 different substituents. If these are kind of A, B, it's going to be quite difficult to tell. So we won't really touch on that. We will later on use carbon NMR, which will help us in some scenarios for this.